Take another 20 seconds. Good morning. Okay. All right. So what I want you to do is swap your paper with your neighbor. You might have to look at the row behind you or something. So this will be real simple grading. You either got it or you didn't, right? So is D proportional to C? I'm seeing some people saying yes and some people saying no. Who wants to go bat for their answer? Mm-hmm. No. No. Okay. Why do you say no?
Because it says that they are the constant rate of change, so they're, as C changes, these changes are proportional, but directly those two variables themselves are not.
Okay. Does anybody want to go to bat for yes? Touche?
I want to say yes because if they vary with the constant rate of change, then one is varying as a multiple of the other. Or
So what's a multiple of the other if we have a constant rate of change relationship?
So I said that the values themselves are not proportional, but the changes in the values are proportional.
Okay, so that's the meaning of constant rate of change. So the answer is not necessarily, right? If they said no, that's fine. No is better than yes. Yes is wrong. If they said no or not necessarily, that's good.
but what if they explained it right and said yes?
Then that's still wrong, right? So changes in D are proportional to changes in C, right? With these being the crazy important words in the sentence, okay? So, so we've been capturing this sentiment for, a while now in a formula. So that's what number 2 is asking for. How do we represent this? Yes. Okay, so delta D is equal to some, the constant rate of change times changes in C. Right? This is what it means to be in a constant rate of change relationship. And so again, these deltas are representing changes. I mean, if nothing else, let's just be really silly about it and remember it's a rate of change. Right? We are talking about changes here. Okay? So how is the constant rate of change computed? I heard what? Yeah, so K is the constant rate of change, and we can solve for it by doing delta D over delta C, okay? So just write a total out of 3 on the top of the paper and turn it into the middle, please. Oh, sign your name as the grader before you pass it in. Question? That's fine. Give him a point. I'm sorry? Yes. And pass in your homework as well. Alrighty. So we are moving forward with what we sort of left off with last time, which is this idea of accumulation. So we were talking about how if we have a function, we can keep track of the amount of a quantity by keeping track of little bits of change in what? The output, right? So we track accumulation of the output of a function as the input changes, okay? And these outputs and inputs are changing by little amounts. We're keeping track of little changes. So a little bit of accumulation can be represented by, what do we usually represent the output with? Y. So a little bit of accumulation would be change in Y, okay? And so if we have a constant rate of change K, then I can compute delta Y, right, the change in Y, by doing what? We literally just did this. Yeah. Right, the change in Y is K delta X, okay? Great, so that's where we're at. Now, we saw this with our tax function, right? We said, hey, I can represent the total amount of tax due if I make $58,000 in a year by using my actual tax function, right, that we worked so hard to develop right here, okay? But I could also think of it in terms of an accumulation of the amount of tax on every dollar I make. As that, as the amount of dollars I make grows, so does the amount of tax I owe, right? So I could keep track of these little bits of changes and add them all up, and that will give me the total amount of tax due, okay? So we can think of this accumulation. Now, it's tax sub 1, tax sub 2, etc., because that's the name of our function, but we could also keep track of, thinking, outputs, the y values, since we're graphing on an x, y coordinate system, okay? And then we talked about how we can simplify our lives a little bit by introducing summation notation, okay? Because writing out 58,000 terms to keep track of the little bits of additional tax that I owe is really not going to happen on a daily basis, right? I'm not going to sit here and do that. So we talked about all of these different symbols or notational device that can help us talk about these things. So here, what am I looking at? This symbol is a sigma, right? And it cues us to think about addition, right? We're adding a whole bunch of terms together. How many terms are we adding together? N terms, right? Because we start at 1 and we go to n. What if this I equaled 1 started at 3? Would I still have n terms? Yeah, it wouldn't be n terms anymore because we're starting at 1. If this was a 3 right here, then we'd be starting at 3, then going to 4, 5, 6, all the way up to n. We wouldn't be looking at n terms anymore, okay? So it's a matter of convenience, if you will, or not necessarily convenience, but coincidence, not even that. I don't have the right word at the moment. But when we start at 1 and then go to n, that happens to be telling us how many terms, okay? But I want you to be aware that it's not always that case, okay? Now, what do the terms look like? If I were to actually write out what each term looks like, what does the first term look like here? R sub 1 delta x, right? And then I add r sub 2 delta x, and we add until we get to r sub n delta x, right? And so when we look at something of this form, what are we looking at? What does this remind us of? So I've got a rate times a change in x. What does that usually give us? A change in y. So this could be perceived as a change in y and another change in y, right? Okay. So depending on what we're looking at, maybe I have a rate function that changes over different intervals. And when I compute this sum, I'm actually computing like this total sum of little bits of accumulation. This would give me a total amount of y after n intervals. Okay. Now, what if I told you that this line was used to represent the same thing as what I've got above it, right? So I want this to have the same meaning as this. If that's the case, what kind of function or what kind of thing does the f of x sub I have to represent? The rate of change, right? These have to represent rates, okay? And so I want to draw this to our attention because there are basically two types of functions that we have considered so far. We've considered rate functions, and then we've considered accumulation functions, right? So when we had our tax functions, for example, we had like tax rate of x. This was a rate function. And then we had tax of x. This was an accumulation function, okay? Does that make sense? How are we feeling about that? Good? Okay. All right, so then going back to the summation notation part, we could shorthand the expression in this way, okay? Okay, so your homework had a rocket-powered basketball. So cool. So this is an animation to help us think about that scenario, okay? I'd like you to take maybe a minute to talk to your neighbor to give as much analysis of this scenario as you can. Like break down every part of it. What's on the x-axis, the y-axis? What are we looking at on the left graph, the right graph? What is this animation showing? Take a minute, talk to your neighbor. All right, shall we bring it together? So, I just think it's great that everybody's having conversations about rockets. It's cool. Okay, so where in this animation should we look to see elapsed time growing? The x-axis? So how would I actually quantify, like, what is the thing representing the amount of elapsed time? The bold black bar down here at the bottom, right? So this bar is representing the elapsed time. Okay, cool. Where in the animation should we look to see the basketball's velocity for the current value of elapsed time? So the red lines. All of the red lines together? Okay, so if we pause, right, because in this world you can pause time, to look at the current value, right? So then, at, I don't know, 5.9 seconds, I'd have to go up to the actual point on the graph, the velocity graph, to locate the current velocity of the basketball, right? So the y value of this red bar is going to give me the basketball's velocity, okay? Oh, uh-oh. So then where should we look to see the basketball's height for the current value of elapsed time? On the y-axis of the right graph, right? And again, if we pause the animation, because we control the universe and we can pause time, then we could actually see, like, estimate where the ball is, right? Okay. But so I'm kind of making fun of this point. What does it actually mean to say the current value of the basketball's height, considering the fact that the ball is constantly moving? Yeah? Okay, so you're saying there is no exact instance of height. Right. So, I mean, we really are imagining that we could pause time and take a snapshot of what's going on and then compute the height. It's almost like you took a photograph of the scenario and saw what was going on. But I do want you to be conscientious of the fact that we are modeling a constantly changing scenario here. So, while we can imagine taking a snapshot in time, the actual situation is constantly changing. Okay. Okay, so just to drill this in, what does a point on the left-hand graph represent? The ball's velocity at that particular time. If we just said the ball's velocity, would that be correct? No. Why? Because it's constantly changing? Hmm. So how is this ball's rate of change behaving? Is it a constant rate of change? Is it a changing rate of change? The rate of change of the rate is constant.
Every absolutely increases by 1 foot per second. Now, the actual distance above the ground changes because it elapsed time that the basketball is traveling.
Okay.
So it's going to be traveling more feet in a given second as the rate increases, but the actual increase of the rate itself is constant.
So you're going into like an acceleration type conversation. I want to focus on, which is fine. I want to focus on actually describing the rate of change, the velocity, in terms of what we've done so far. Is there a way that we can describe this situation using what we've done to date? What kind of function is this? It's a piecewise function. And the pieces are? Mm-hmm. And what's the behavior there? Is it changing within each half second? Is the velocity changing within each half second interval? No, right? It's constant. That's why these are horizontal. So within each half second interval, the rate of change is a constant. This is a piecewise constant rate of change function. Is that resonating with what we've done so far? Yeah? No? Okay. Well, we'll keep talking about it. So let me come out of this for a second and come to graphing calculator. Okay, so I've got this animation again, this time in graphing calculator. Mark, how did you say that I could get it to not go backwards? When I press play, option? Okay, thank you. So here's the same animation we've been looking at. I'm going to press my slider button over so that the right-hand graph is no longer just tracing out heights along the y-axis. It's instead going to actually graph the accumulation of height as time elapses. So can you talk to your neighbor or think really hard to yourself about what it will look like when I do that? Does the scenario make sense? I'm gonna now let time elapse horizontally. So what is that gonna look like? All right, I'm gonna do it. Are you ready? Ready, set. Is this what you expected? Is this a curve? Looks curved. I'm getting resistance from the side of the room. It looks like a curve, right? Is it? No. Good. Why? I'm zoomed out too far. If I zoom in, what happens? What's wrong with? Hold on. Oh. That black bar just got really big. Hold on. That was the keeping track of the lapse time bar. Let's see. Okay. So now you can see that this is actually made up of straight lines, right? So are we surprised by this? Can somebody explain to me why it's happening the way it is? Why is the right-hand graph made up of linear pieces? Yes. Okay, so for each half-second interval, the rate of change is constant. So correspondingly, the height of the ball can be modeled with a linear function within each piece, right? Okay, so if I pause this for a second. So now if I wanted to actually represent, well, actually, let me make you do some work really quick. So how would you write a function to represent the ball's height at any time during the first, like, 1.5 seconds. Okay. So I want a function h of x that will tell me the height of the ball at any moment during the first 1.5 seconds. Yeah, Rochelle? All right, it will indeed be a piecewise function. And we know that because we can see there are 1, 2, 3 pieces during the first 1.5 seconds. Okay, how do I write the equation? What should each piece look like? A linear function, right? What's our form for linear functions? We've got our new y value equals rate of change times the change in x, right? So this is the change in y, and we add that to whatever the original y value was, right? The old y value. Okay. So if I'm looking at the first half-second interval, what equation can I write? What's the rate of change? 0. So I could keep going. That's boring. 0 works, right? Okay, and this works for x between what? 0 and 1/2, right? Okay, now it gets a little more interesting. What about the second half-second interval? What's the rate of change? Yeah.
I was wondering if this one is easier than homework.
Uh-huh.
For that first line,
Yes.
you have less than or equal to equal 4.5.
Uh-huh.
Shouldn't it just be less than because the next rate changes at the next line?
So the reason why I include this half-second here is because I'd like to be able to define the next line recursively, if you will. So you could, I mean, right up until that moment in time, right? That, I mean, this is still accurate, right? Like the ball hasn't gone anywhere. So I don't know if I'm actually answering your question right now. Yeah?
As like it was modeled in our homework as like if it was, you know, in the tax equation, it's if it's, you know, $499.99, if
Right.
you're in the lower bracket, as soon as you hit that upper bracket, that gets taxed at that amount. So wouldn't that be the same here? As soon as you hit half a second, the rate changes.
It does. Interesting. Let me think about that, because right now my answer is I do it this way because it makes the function work, which is really dissatisfying. So let me think about it and I'll get back to you. Okay. So for now, let's keep it with including the half second, and then knowing that, you know, the rocket fires, and then, you know, so it fires at half a second. So then after that, its rate will be what? 1, right? And then we're starting this at half a second. And then the height of the ball, when that kicks in, is the height at half a second. Okay. And then we could do it again. So now the rocket fires at 2 seconds. And so for any amount of time after that, within the next interval, we can get the rocket's height, or the ball's height, using this. Okay? Okay? All right. Can I move on? Is this okay? All right. So then Okay, so then what we're reaching for, what we're going for, is that once again, just like with the tax function, we can represent the height using a single function, building it just the way that we had started to, right? So if I wanted to keep going, I could keep going and end up with a function that would allow me to define h of 6, right? I didn't get that far. I only got up to 1.5 seconds. But I could really think of, this amount of height as an accumulation of height accrued over small intervals, okay? And so when we look at this, our changes in x are half-second intervals, and we've got corresponding changes in y, right? Changes in height. So how would I represent a change? Let's say we're at 2 seconds. How would I represent a change in x of 1/2 visually? How do I represent that? I'm seeing one of these. So a horizontal line, right? So that would be a change in x of 1/2. How do I represent the associated change in height? With a vertical line, right? And how would I compute that value? So k times delta x. Do I know what k and delta x are? I definitely know what delta x is. Can I figure out what k is? So I started at time is 2. X is 2. Yeah. 4. How'd you get it?
You increase by 1 feet per second for each half a second.
Okay.
So basically, 2 divided by half is 4. So after 2 second time, you have 4 feet per second.
Okay. So you've done a lot of work, which is fine if you like doing work. I'm significantly lazier about it. I've got a rate function right here, right on the left of the screen. This is the rate function. It will tell me exactly what the velocity is at any given moment in time. So if I'm at in a 2 second to 2.5 second window, I can look here and figure out, oh, the velocity of my basketball is 4, right? So I can get this value by looking at the rate function on the left. Okay, so we can compute this value. Now I could keep doing that, right? I could have another half-second change and another corresponding change in h or y, however you want to think of it, and we can keep going, right? And notice that the changes in height are changing. Why is that again? Because the rate of change is changing, right? The rate of change is increasing with each passage of a half-second interval. So if I wanted to keep track of those changes, I can, right? So each change in height, I sort of didn't totally line it up, but each change in height, right, we can compute by doing the rate of change times the change in time. And that will give it to us. And then if we want to know the total height up to a certain point, what do we do with these values? What do I do with the values? Yeah. We add them together, right? So all of these little changes in height added together will give me the ball's actual total height, right? How far has it traveled? So we can represent, an accumulated distance for example, right, the first 11 intervals in this fashion. We can shorthand it using our summation notation, okay? But really the thing that I want you to take away from this conversation is, right, we can get the total value by thinking about accumulation of little bits of change. That's what we're getting at here, okay? And so this is just a convenient notation for doing that. We're going to skip this for now. Okay, so bringing it all together once again. So what's the big picture here? Calculus addresses two fundamental issues. I told you this on the first day of class, right? So we've got one scenario where you know how much of something you have and you want to know how fast it's changing. The other scenario that calculus addresses is that you know how fast something is changing and you want to know how much of it there is. Which scenario have we been looking at so far? Take a second to think about that. Can I get fingers? 1, 2, 1, 2. I've got some non-committers. Okay, so I'm seeing more 2s than 1s. Who wants to give an explanation for why they picked 2? Yeah.
It gave us like the rate, like every single half second it increases by 1. We know how fast it is changing.
Okay.
And we want to know how much of it there is, how much height of the basketball there is. So we were 2.
Okay. So with the basketball scenario, the information that was given to you to start with was, how does the rocket work? It, increases the velocity of the basketball in half-second intervals. And then from there, we built up figuring out how much height the basketball actually achieves. So we went from a rate to an accumulation. That is scenario number 2. Okay, that's what we've been doing. So if any of you have misconceptions about that, then we should definitely talk to each other, okay? Sooner rather than later. So if you've taken calculus before, I'll mention these words. The first scenario we address with the derivative. That's something that we haven't gotten to yet, and probably your friends in other calculus classes have. I know I got an email about a mastery test. I'm still coordinating with the department to see how we're going to do that, but obviously we are not there yet. So, that will come later for us. Instead, we're starting with this idea of integration, okay? But that's the conventional label that people put to this idea. I'm not putting this up here because I want you to go back and look up in your old notes what integration means. Please don't do that because it will not align with the things that I'm trying to achieve here. But this is what I want you to think about when I say the word integration, okay? So the idea behind it is that the value of a quantity can be calculated as the sum total of many little bits of change, okay? So it's just, integration to me is this idea of accumulation, okay? How are things accumulating in little bits, okay? So we saw that with the tax function, right? So I can talk about a sum total. How much do I owe in taxes by thinking about accumulating over little bits of change, okay? We did this with the height of a basketball, where again, I could have a function that spits out the total value, but I could really think about achieving that value by computing little bits of change, okay? I feel like I should pause for a second to really let that sink in. Okay, so where are we going next? Okay, the scenarios that we've seen so far have all been such that I give you a rate of change function that's piecewise constant, right? But that's not necessarily how everything in the world works, right? Sometimes you can have a scenario in which the rate of change isn't constant or even piecewise constant, right? The rate of change might be changing in a very smooth fashion, okay? Rather than these jumpy discontinuous intervals that we've been seeing. Okay, so so we've dealt with the nice scenarios, but this isn't always the case. So how can we use our tools to study scenarios in which the rate of change isn't behaving as nicely? Okay, so so I've got a scenario here, and basically, so this is an introduction to your homework for the weekend. Okay, so we want to imagine that we have a ball that's hanging from a rubber cord with, you know, like some sort of board above it, and we're going to push the ball downward. And so the rubber cord is going to stretch, and the ball is going to bounce up and down. Okay, and so I've got a graph here on the right that's showing the ball's velocity as it's moving away, you know, relative to moving away from the board X seconds after it's been pushed. Okay, so you might recognize this function. This is the cosine function. So we're, once again though, that's sort of interesting. But I'm handing you a velocity function, right? I'm telling you how this ball's velocity is changing. This is a rate of change function. It is very much not piecewise constant, right? So how might we apply the tools that we've developed so far? What are the tools that we've developed so far? How have we dealt with scenarios? Too big a question? So what's the only scenario we've dealt with so far? Given a rate, trying to find quantities. Okay, we can be more specific because the type of rates that we've looked at have been very, very specific. They've been constant, right? So this is definitely not constant. But what I can do is approximate this scenario with little pieces of constant rates of change. Okay, so I could imagine taking this rate of change at the beginning, and maybe I should do it in a different color, approximating the rate of change over an interval, and say if I only look at half-second intervals, then I could approximate the rate of change by using this value right at the beginning. And then I could do it again here. And then I could do it again here. And again here. It's not exact, right? I'm no longer keeping track of the exact rate of change at every moment in time, but I can approximate the rate of change over small chunks of time. Okay? So that would look something like this. So small chunks of time pass. I can approximate the rate of change over each interval. It's not perfect, but it'll get me somewhere. And then the idea is that we're going to take these chunks, right now it's in half-second chunks, right, that I'm approximating, and realize, well, that's not so good. Can I do better? How would I do better? Smaller changes, right? So instead of dividing this up by half-second intervals, I could divide it up into 1/10 of a second intervals, or 1/100th of a second intervals, and we can get better and better approximations. Okay, so but as soon as we introduce this idea of having a constant rate of change, then I can go and actually build the height of the distance traveled of my ball as a piecewise linear function, right? Because I've got constant rates of change to work with. So we're going to talk about this a lot more. Your homework over the weekend is going to be reading on this, and so process that, digest it. Don't wait until Monday morning because it's deep. Okay, so have a wonderful weekend.